Now, in earlier sections, earlier, like this is college algebra back in intermediate algebra, we were able to take zeros like something with zeros of -2 and 3. And we were able to build the polynomial from it. So if zeros of -2 and -3 existed, that means x equals -2 and x equals 3. That would come from x plus 2 equals 0 and x minus 3 equals 0, which would come from x plus 2 times x minus 3 equals 0, which comes from x squared minus 3x plus 2x minus 6 equals 0, x squared minus x minus 6 equals 0. So our original function would be f of x equals x squared minus x minus 6. So from the zeros, we're able to build back all the way to the function. Now, what we're going to do here in college algebra is this same type of problem. But we're going to make it all weird. Zeros of 2/3 and 4 plus 2i third degree polynomial with integer coefficients. Integer coefficients means we got to take this all the way. We can't leave it in factored form. So third degree means that when we have our integer coefficients, x cubed is going to be the highest power of x we have. It means we're going to have 3 linear factors. Here's a 0 of 2/3. Here's a 0 of 4 plus 2i. What do we get as a bonus? 4 minus 2i. 4 minus 2i will be a bonus. So let's see what we can do with this information. If I have zeros, if I have a 0 of positive 2/3, that means x minus 2/3 is a factor. If I have a 0 of 4 plus 2i, that means x minus 4 plus 2i is a factor. And then the bonus one of x minus 4 minus 2i would also be a factor. So now we just multiply. Want to multiply this stuff out. First, x times x is x squared. Outer, x times negative 4 minus 2y minus x times 4 minus 2y. Inner, minus x again times 4 plus 2y. Last, negative times negative is positive, and it'd be 4 plus 2y times 4 minus 2y. Okay, so this is just me foiling this out. The steps of FOIL are more complicated because we have very complicated looking things. First, x times x. Outer, positive x times negative that thing. Positive times negative is negative. Again, negative this thing times x minus x times this thing. And then negative times negative is positive. These two things. Expanding in here. X squared. Let's distribute a minus x. Minus 4x. Negative times negative is positive. Plus 2xi. Here, negative x times 4, negative 4x. Negative x times 2i, negative 2xi. Plus difference of squares. 4 squared minus 2i squared. Or you can first outer inner last that as well. But I know if I multiply two conjugates together, it's a difference of squares. The plus 2xi and minus 2xi cancel out. I have x squared minus 4x minus 4x, that's minus 8x. 4 squared is 16, so this is plus 16 minus 4i squared. I squared is negative 1. So this is minus 4 times negative 1. That's 16 plus 4. 16 plus 4 is 20. Wow. So that means this times this, after we do all that work, this times this is actually x squared minus 8x plus 20. Now let me copy this line up top and we'll keep going. And we don't need it to say equals 0 anymore because we have a function at this point. X minus 2/3 times x squared minus 8x plus 20. Now, there's a very important step that I have missed to now. It's not so much a missed step. It's something that's going to make this a lot easier and get rid of the fraction. Now, remember before when I said, you know, if we have something like x minus 2 times x plus 3, that gives us zeros of x equals 2 and x equals negative 3. Now imagine we had a number out front, a number like 3. That doesn't change what our zeros are, because we would get 3 equals 0, and we can't solve that. It's a false statement. It doesn't have x. It's just garbage information. What we can do is put some number in front. It can be any number we want, and it won't affect the zeros. I'm going to put a 3 there, and I'll show you why in a second. Because the 3 in front doesn't affect the zeros we had, but I can multiply it through and turn this into 3x minus 2. And that is nice compared to having to multiply a 2/3 through everything. You can choose a 6 or a 9, anything that makes it nice. This is not going to be a unique answer. A 6 will give us a different answer, but it won't affect the zeros that we started with. So then we multiply the 3x through everything. 3x cubed minus 24x squared plus 60x. Then the minus 2 through everything. Minus 2x squared plus 16x minus 40. So we end up with f of x equals 3x cubed minus 26x squared plus 76x minus 40. So those weird looking zeros we had before, this would be a function with integer coefficients of degree 3 that has those zeros. Let's do another. Find g of x of lowest degree with zeros of negative 2, multiplicity 1, and 4, multiplicity 3, satisfying the condition g of 0 equals 256. So last time we started with our zeros. We didn't think about putting a constant in front of our factored form until we needed one to get rid of the fractions to make things easier. Here, they're giving us a specific condition. In addition to being the lowest degree with these zeros, it must satisfy this point. When x is 0, the function is 256. G of 0 equals 256. This means we need to take into account our extra constant in front of the factored form from the beginning. So g of x, polynomial with lowest degree. That means a multiplicity of 1, a multiplicity of 3. That's going to be 4 total. So an x to the 4th is as high as we're going to go here. So g of x is going to be some constant a times a 0 of -2. That must come from x plus 2. And since it's a multiplicity 1, it's going to be x plus 2 single factor, first power. A 0 of 4, that's going to come from x minus 4. This is a multiplicity 3, so it's coming from a third power. Satisfying this condition that g of 0 has to be 256. That means when we plug 0 in for x, we're going to get 256. So this is a times 0 plus 2, 0 minus 4 cubed. 256 is a times 2, -4 cubed. -4 cubed is -64 times 2 times a. That's 256. We're going to use this information to solve for a. We're going to find what the specific a has to be. 2 times -64 is -128. And if I divide both sides by -128, I get that a is -2. A is -2. Times x plus 2 times x minus 4 cubed. So we need to multiply this out now. A cube that's something times itself 3 times. X minus 4 times x minus 4 times x minus 4. So I'm just going to multiply 2 of these together at a time until I'm all done. X minus 4 times x minus 4 here. That's going to be x squared minus 8x plus 16. Then I'm going to multiply this x minus 4 through. I'm going to get x cubed minus 8x squared plus 16x minus 4x squared plus 32x minus 64. Combine like terms, thank goodness. Give me my space back. X cubed Negative 8x squared minus 4x squared, that's minus 12x squared. 16x plus 32x, that's plus 48x, minus 64. Let me write this up top so that I have room to work. Negative 2 times x plus 2 times x cubed minus 12x squared plus 48x minus 64. I'm going to multiply this x plus 2 times everything. So the x through gives us x to the 4th minus 12x cubed plus 48x squared minus 64x. And then the 2 through everything is plus 2x cubed minus 24x squared plus 96x minus 128. Combine the like terms. Negative 2 times x to the 4th minus 10x cubed. Negative 12 plus 2 is negative 10. 48 minus 24, so plus 24x squared. Negative 64 plus 96, that's positive 32x minus 128. And now I'm going to multiply that negative 2 through. We get g of x equals negative 2x to the 4th plus 20x cubed minus 48x squared minus 64x plus 256. And that is the answer. Okay. Let's consider this function. We're not going to do much with it, but we're going to consider it. F of x equals x to the 5th minus 18x to the 4th plus 128 x cubed minus 450 x squared plus 783 x, ran out of room, minus 540. Wow. Now, sometimes finding the zeros of a polynomial may be near impossible, let alone difficult. For instance, here, if we were to apply the rational zero theorem, P would be all the factors of 540. I'm not going to write these down, but I'm going to read from this list over here. Plus or minus 1, plus or minus 2, plus or minus 3, 4, 5, 6, 9, 10, 12, 15, 18, 20, 27, 30, 36, 45, 54, 60, 90, 108, 135, 180, 270, and plus or minus 540. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and it's positive or negative, that's 48. Thank goodness our Q is just 1, so we don't have to divide for our P over Q, but that's a lot of possible rational zeros to check. But in a little bit, we're going to introduce something called the upper and lower bounds theorem. And first, we're going to talk about something called Descartes' law. No, Descartes' rule of signs. And these are going to help us narrow down the ranges that our zeros could be in, so that we don't have to look through 48 different possible rational zeros. Now, we're not going to actually do anything with this function. Like I said, we're just going to consider it. But we will look at 2x to the 6th minus 3x to the 4th minus x cubed plus 5x squared minus 6x minus 4. And what we're going to look at here, let's look for sign changes. What do we mean by a sign change? A sign change here is going to be anything that changes from a positive term to a negative term. Anytime we change from a positive to a negative, we have a sign change. Or change from a negative to a positive. That would be a sign change. So how many sign changes do we have here? Well, positive 2 to negative 3. That's one sign change. Positive to negative. And this is negative to negative, so that's not a change. But here's negative to positive. Negative to positive. That's another sign change. And then positive to negative. Positive to negative, that's another sign change. Negative to negative, that's not a change. So here we would have 1, 2, 3 sign changes. Descartes' rule of signs tells us potential numbers of positive or negative real zeros. And quite honestly, it's very confusing until you see it worked out, and then it's still confusing. But by the end, you'll see that it's kind of just intuitive. I'm going to explain why the different pieces work, and we'll see how useful this can be to us in the long run. By the time we use an example, we should probably have a little more practice in sign changes. So let's do another, just count the sign changes and we'll go from there. Let's do f of x equals x to the 5th minus 6x to the 4th plus 12x cubed minus 12x squared plus 11x minus 6. Ha! Well, positive to negative, negative to positive, positive to negative, negative to positive, positive to negative. So the most sign changes we could have had here, we have 1, 2, 3, 4, 5. Five sign changes. Descartes' rule of signs, and let me write this out. Wonder how many people literally were thinking of a cart when I was saying Descartes, Descartes. Nah, it's just French. Descartes' rule of signs. The number of positive real zeros is either the same as the number of sign changes, or less by a positive even integer. So the number of positive real zeros is either the same as the number of sign changes, so it could be 5 positive real zeros, or less by a positive even integer. Let me clear this up for you. Even integers, 2, 4, 6, 8. So it's either 5 or less by 2, 3, or less by 4, 1. So 5, 3, or 1. Hopefully what I'm about to say is going to make that click into place and make you go, well, duh, if it can be the same, of course, if it could be 5, it could only be 3 or 1 if it's less than 5. Because if it's not a real zero, then it's a complex zero. It's got I in it. And what do we know about complex zeros? They always come in pairs. So we can't just have one complex zero, because if we have one, it comes with its conjugate. It comes with its freebie, its other pair, the other part of the pair, its partner. So if we could have 5 positive real zeros, if 5 is a possibility, then we can't have 4, because if we had 4 real zeros, the 5th would be a complex, but that complex would come with a partner, which means there would be 6 overall. One complex actually means that there's 2. So if it's a number of positive real zeros less than 5, it can't be 4, but it could be 3. It could be 3 plus a pair. Or it could be one real zero plus two pair of complex. So the number of positive real zeros is either the same as the number of sign changes or less by a positive even integer. So notice this is only for positive. There is a second part of Descartes' rule of signs. And the second part, you guessed it, is going to refer to the number of negative real zeros. The number of negative real zeros is either going to be the same as the number of sign changes. It's going to be different now. The same as the number of sign changes in f of negative x. F of negative x, so not the number of sign changes in the function. We've got to find now f of negative x and do the sign changes there. So f of x had 5 sign changes. How many sign changes is f of negative x going to have? Well, we'll get there in a second. There's a second part. Or less by a positive and even integer. So again, less than the sign changes in f of negative x by a positive even integer. So by less by 2, less by 4. And remember, why is it less by 2, less by 4? It's because if it's less 1, that 1 must be complex, but that complex comes with a pair. So it can't be less by 1. It has to be less by pairs. So let's find f of negative x. We would have to plug negative x in for x everywhere, and then figure out what happens when we apply the 5th power, the 4th power, the 3rd power. Remember, a negative raised to an even power becomes positive because negative times negative is positive. There's pairs again. Pairs of negatives become positive together. A negative to an odd power stays negative because each pair becomes positive, and then the odd one out at the end would turn it back negative. So f of negative x would simplify negative to an odd power, negative x to the 5th. Negative to an even power would be positive x to the 4th. Negative to an odd power changes this plus to minus 12x cubed, because negative x to an odd power stays negative. Negative times that positive 12. Negative times positive is negative. Here, the negative x squared would turn positive. So that minus 12 stays a minus 12 because it's multiplied by the positive x squared. Then here, no power. So positive 11 times negative x, positive times negative is negative 11x minus 6. So we found f of negative x. Let's count the number of sign changes. We're starting negative, negative to 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 negative. There are no sign changes. No sign changes in f of negative x. So Descartes' rule of signs tells us that means there are no negative real zeros, because it could only be the number of sign changes or 2 less or 4 less or some even number less. So what Descartes' rule of signs allows us to do tells us the number of positive real zeros, number of negative real zeros, and the number of imaginary zeros. There could be 5 positive real zeros, or there could be 3, or there could be 1. We know that there's 0 negative real. If there's 5 positive real zeros, well, since this is 5th power, we can't have more than 5. That must mean that there would be 0 imaginary. If we had 3 positive real and no negative real, that must mean that there are 2 imaginary. Or if there's 1 positive real and no negative real, that means there would be 4 imaginary, because the number of real zeros and the number of imaginary complex zeros would have to equal the total number of zeros, which is the degree, in this case, 5.